The last thing that we looked at, correct me if I'm wrong, was like a vertical asymptote. I gave you an equation and I said to find the vertical asymptote, and we simplified some things before we determined what the vertical asymptote was. So this is still section 2.4. So somebody that took good notes, what was the last example number we did? I don't remember. Was it 3? Oh, 5. Oh, I'm way off. All right, so let's look at one more where I want you to find the vertical asymptote. And let's say the function that I want you to look at is 3 times parentheses x minus 6, and then over x cubed minus 36x. Okay. So our process for finding vertical asymptotes is always to simplify first and then see if what would make the denominator 0. Okay, so notice the top is already factored for us. We don't have to do a whole lot of work on that. Okay, what about the bottom? Normally speaking, we're not comfortable factoring cubics usually. Okay, but this one, what do you notice both of those terms have in them? An x, right? So if we factor out an x, we get x squared minus 36. Okay, but then we should be comfortable further factoring that guy, right? Because that's one of our special cases that we talked about even last time, right? That's a difference of 2 what? 2 squares. So we've got 3 times x minus 6 over x times x plus what? What's the square root of 36? 6, right? And then x minus 6. Kind of ran out of room on my paper there. Okay, so then what? We're not quite ready to determine what the vertical asymptotes are. What do we need to do first? We need to simplify, right? So we cancel those out, okay? And so it looks like we actually only have 2 vertical asymptotes instead of 3, okay? So what are they? You can't forget this guy, so we have to set that equal to 0. So x equals 0 is a vertical asymptote, but also what? What would you get if you set that equal to 0? Negative 6. Okay, so the gist is make sure you simplify first, okay, and then determine what makes the denominator 0. All right, so you'll talk about this more in the next class in Business Math 2, but just so you know, this point where we crossed out this x minus 6, it actually means that there is a hole at x equals 6. Okay, there's a hole in the graph. You remember those graphs that we've looked at occasionally where there's like an open circle in the middle of it? That's what that tells you, okay? So anything, anywhere that gets canceled out, there's a hole there. So I'm going to say any part that is canceled indicates a hole. So while it's not a vertical asymptote, it's still a significant part of the graph, even though we're simplifying it kind of out of there. Okay, so we talked about vertical asymptotes last time, just reviewed one example using vertical asymptotes, but you can also have a horizontal asymptote. So I'm going to abbreviate that HA, just like I abbreviated vertical asymptotes VA. Okay, so horizontal asymptotes are a bit different than vertical asymptotes, not just in the fact that we're talking about a horizontal line. They are not as concrete as vertical asymptotes, and let's talk about what I mean by that. So it's a boundary line that the graph approaches, but the disclaimer here is it's only at the ends. And we'll do some examples, and I'll show you what I mean by that. But it doesn't touch or cross. In other words, we only care about the far left and the far right, okay? So when I say at the ends, that's really what I mean. The middle or the center of the graph does not necessarily have to follow the horizontal asymptotes rules, okay? Vertical asymptote rules are more concrete. The graph never crosses or touches or crosses the vertical asymptote. Horizontal asymptotes are a little bit of rule breakers. All right, so in algebra, we find the horizontal asymptote using 3 cases. Okay, so you look at the degrees of the numerator and denominator. And then there are 3 possibilities once you compare the degrees of the numerator and the denominator. Remember, what's the degree again? We talked about that on Wednesday. So the degree is the highest what? Exponent slash power that we have, right? So it's the highest power on the top versus the highest power on the bottom. And so here are your 3 possibilities, okay? If the numerator degree is bigger, then there is no horizontal asymptote at all. Okay, so that means if the power on top is anything bigger than the power on the bottom, okay, there's no horizontal asymptote. Okay. If the opposite is true, so if the numerator degree is smaller, then the horizontal asymptote is always at 0. Okay, notice vertical asymptote equations look like x equals a number because that's what vertical line equations are, and then horizontal line equations are always y equals a number. And so the only case we haven't covered is if they have the same degrees. Okay, so if they have the same degree, in other words, maybe you have a cube over a cube, okay, then the horizontal asymptote is going to be found by doing the following. The horizontal asymptote is going to be y equals the leading coefficient of the numerator over the leading coefficient of the denominator. Okay, that sounds more complicated than it is. It's actually not going to be difficult at all. Okay, now when you get to the class after this one, which is business calculus, we're going to talk about a calculus way to find asymptotes. Okay, but for now, we don't know that and we don't need to know that. Okay, so you're going to need to kind of remember 3 cases. Okay, there's either none, it's 0, or it's some combination of the top over the bottom. Okay, that's the only 3 options. Okay, so let's practice one. I say one, let's practice one with some multiple equations.
Wait, is this example?
I don't really know why I said 4. Yes, 7. Yes. I'm going on my old numbering system, which is clearly off.
Sorry.
Yes, no, you're good. All right, so I'm going to do 3 wide here, okay? So just to kind of save some space. So we're going to do x squared minus 4 over x cubed plus 2. We're going to look at x cubed plus x to the 4th over 3x cubed. And then thirdly, we're going to look at negative 4x to the 4th plus 4 over, let's see, which one have I not done yet? 3x squared plus 2. So if I asked you to find the vertical asymptote, how would you do that, just in words? You would simplify and then set the what? How do we find vertical asymptotes? I'll wait. I know somebody knows. It's just Friday and you don't want to say, right? So look up in your notes if you need to. How do we find the vertical asymptote? We simplify and set the denominator equal to what? Equal to 0. Okay, but horizontal asymptote is different, right? We follow these 3 rules. Okay, so the answer is either going to be none, 0, or some combination of top over bottom. That's our only options. Okay, so let's look at A, for instance. Okay, so what do you notice about the degree on top compared to the one on bottom? Yeah, the degree on top is smaller. Okay, so look back up at top, right? Which case is that then? Is it case number 1, 2, or 3? 2? Okay, so that means the horizontal asymptote is y equals 0. Okay. If the power is anything smaller. Now notice in this one it happens to be 1 degree smaller, but if it was anything smaller at all. So it could be a 5th power on bottom and a 1st power on top. Okay, and it would still be, the horizontal asymptote would be 0. Okay, so what about B? What do you notice about the powers or the degrees? They're the same? Okay, so since they're the same, then we do have a horizontal asymptote, and it's going to be y equals the leading coefficient of the top, right? Remember, leading coefficient is that number in front of the highest exponent term, right? What's the understood number? Well, actually, I did this one a little off. We're going to change the second one, but so the degrees aren't the same. So what did I do wrong? Which I didn't do on purpose, but it's a good thing for you to look out for when you do your homework. The degrees actually aren't the same. I paid attention to only the first term, right? Which was a mistake on my part. So actually what's true? The degrees aren't the same. What is true instead? Yeah, the numerator's bigger, so watch out for that. I even fell for my own trick there, honestly. So actually the degree on top is bigger. So what does that mean then? It means there's not one, okay? There is no horizontal asymptote. So on your My Math Lab homework, there will be a multiple choice option for you to choose none. I don't know why the lighting is so bad. It's because I wrote over white out and it's glary, but anyway, that's supposed to say the degree on top is bigger, so there's no horizontal asymptote. So then here, I want to change this to a squared just so we have all the cases. So on C, go ahead and change that to a squared power instead of 4th like I had it. Just so we have one of each. All right, so now what do you notice about this one now that I've changed it? The degrees are the same. So there is a horizontal asymptote. And it's going to be y equals, pull the leading coefficient of the top and put it over the leading coefficient of the bottom, right? So what's the leading coefficient of the top? What is the number in front of the highest exponent term? -4. And what's the number in front of the highest exponent term in the bottom? 3. So we have a horizontal asymptote, and it's just equal to -4/3. In other words, there's a horizontal line at -4/3 that the graph at the ends gets close to but doesn't cross. Okay, so just to kind of regroup, okay, so we're going to do a problem where we have to find a whole bunch of different components of a graph. Okay, so let's just run through how we find all of kind of the important pieces. Okay, so if I ask you to find an x-intercept / x-intercepts, how do you find it? Always, regardless of what kind of function it is. Yeah, you set y equal to 0. Okay, what about y-intercept? Set x to 0. Okay, a vertical asymptote, if there is one, how do you find it? You simplify, then what? Set the denominator to 0. And then for horizontal asymptote, we compare the degrees of the top and bottom, or the numerator and the denominator. And how many options do we have? 3? Okay, so in a nutshell, we should be able to kind of sketch what these graphs would be, okay, using these pieces of information. And maybe we have to pick a few other points. So let's say that I want you to use the intercepts the asymptotes and maybe additional points if necessary. To sketch this graph. F of x equals 2x squared over x squared minus x minus 6. So rational graphs have different looks to them, okay, and they're going to have a lot more going on than polynomial graphs. Okay, polynomial graphs are smooth and curvy. Rational graphs typically are not continuous and they have curves, but they skip over certain spots. All right, so let's just run through kind of the list of things. Okay, first let's find the x-intercept, and we already said what we would do there, right? We're going to set y equal to 0. Okay, so you're going to set this rational function equal to 0 essentially. But notice we're not allowed to have the bottom be 0, right? So ignore this ugly looking fraction. How do you make a fraction equal to 0? Like, give me an example of a fraction with numbers that equals 0. So you can't have 0 on bottom, right? So what's 0 over 5? 0, right? What's 0 over 10? 0, right? So 0 where makes the fraction 0? On the top, right? So in other words, that's really all we need to do here. We just need to set the numerator equal to 0. Because if the top is 0, then the whole thing's 0. So that's pretty easy. So we'll just say, okay, 2x squared equals 0. Okay, don't overthink that. You can divide by 2 and then square root it, but what's it going to have to be if it's just 2x squared equal to 0? What's x going to have to be? 0. Yeah, x is 0. Okay, or if we wanted to list it as a point, it would be the point 0, 0. So I'm going to kind of circle my pieces as I go. So we know it crosses through the point 0, 0. All right, let's move on and find the y-intercept. We do that by setting what? X equal to 0. So we're going to do 2 times 0 squared over 0 squared minus 6. Or sorry, 0 squared minus 0 minus 6. But we kind of already just talked about this, right? We don't even care what the bottom's going to be, although it'll be negative 6. But what's it going to be? What's 0 over negative 6? Just 0, right? So we end up getting the same x-intercept and y-intercept. Okay, in other words, they both cross their particular axis at 0. All right, let's find the vertical asymptote and see what we have. Okay, so let's rewrite the function and see if we can simplify it at all. So we've got 2x squared over x squared minus x minus 6. Notice the top is just one term, so there's nothing we can do to simplify the top, but could we possibly factor the bottom? Yeah, I think we probably could. So we get 2x squared, right? Remember, we can use AC method, but I don't know that we need to because the coefficient in front of x squared is just 1. So we're really just looking for factors of negative 6 that do what? When we factor this, what are we looking for? Factors of the last number that add up to what? The middle number, right? So factors of negative 6 that add up to negative 1. So what would those be? Yeah, minus 3 and plus 2. Okay. Notice we can't simplify here. There's nothing we can cancel out or anything like that. If there was, then we would do that. Okay, but there's nothing to simplify. So if we're trying to find the vertical asymptotes, then what do? Just set x minus 3 to 0 and what else? X plus 2 to 0. And so we're going to get 2 vertical asymptotes. One that is 3, right? And one that is negative 2. And then last but not least, let's talk about the horizontal asymptote, and then we're going to see if we can sketch a graph of this. So again, we have this for our function. Okay, so remember this is where you look at the 3 cases. So what do you notice about the powers of the top and the bottom? The powers are the same, or the degrees. So when they're the same, there is a horizontal asymptote, and how do you find it? you just pull the top leading coefficient, put it over the bottom leading coefficient, right? So you would get y equals 2 over what? 2 over 1 or just 2? Okay, so let's see if we can kind of put all of this together in a graph. So I'm going to go out 5 in every direction. If that's not enough, then we'll extend it later. Let me slide that over. Sorry about that. Okay, so I know that it crosses the x and y axis at 0, 0, so I'm going to put a pretty distinct point there. And I also know that it has asymptotes. Do you remember how we drew asymptotes last time? Yeah, we do like a dashed line because it's not actually part of the graph, right? So we have a dashed line here, and then here. But then we also have a horizontal one where? Up at 2. Okay, so I think it's pretty obvious that I don't have what I need to be able to graph this thing, right? Like I only know one point, and then I know some boundary lines that the graph is going to stay in. Okay, so here's where we can pick some additional points, and we're going to use our calculator in order to do that. In other words, we really kind of need to know what's it doing in the left section, what's it doing in the middle, and then what's it doing over off to the side. Okay, so we're going to pick some points, but we're also just going to use our graphing calculator to kind of help us out here. Okay, so let's talk about how we would enter it first thing. Okay, so anytime you have more than one piece, put parentheses around it. So it's not very important that we put parentheses around the 2x squared because that's just one term, but it won't do it right if you don't put parentheses around the bottom. So we've got x squared minus x minus 6. Okay, if you decided to also put parentheses around the 2x squared, that would be fine. It's just you don't have to have them. You must have them on the bottom because there's more than one piece. So I'm going to look at the graph just to kind of get an idea of what it's going to look like. But then I'm going to look at my table function because I think it'll help. Notice it does go through 0, 0 just like I thought. Also notice it's in how many pieces, which we kind of could have predicted if we looked at our asymptotes. It's in 3 pieces, right? And that makes sense if you think about that there has to be something in every section. Okay. All right, so you can also, when you graph something, go second graph and look at a table. And here, I know it's hard to see, okay, but here it'll just kind of pinpoint where some values are for you, okay? And I like to pick points that seem a little more pleasant for me to graph. Okay, we're just going to sketch the graph, but I wanted to call attention, and I know, again, if you're in the back, you may not be able to see. But what do you notice it says at -2 and 3? If you're in the front, maybe not the back. It says error, and why does it say error at those points? Because that's where the what are. That's where the asymptotes are, okay? The graph is not represented there, so it says error, okay? So I think we can kind of pick out some of the points if we want. For instance, like I would go through here and kind of pick some pleasant points. So it looks like -3, 3 is on my list. So -3, 3 is here. And then if I want to, I can kind of use my graph. Let's go back to the graph. We're going to go back and forth. So it looks like my graph does kind of this. Okay. So what I did is I went and used the table and pulled like one significant point out, and then I just kind of drew it. The center section kind of looks like a sort of parabola-ish thing. So we'll go ahead and draw that. We already have one point in the center anyway. And then I'm going to go back to my table and maybe find a point over here. It looks like none of these are really all that nice. So I'm going to scroll down and see if I can find any. So it looks like 6, 3 is somewhat nice. It's like I'm scrolling down my table until I find ones that look like I actually might want to graph that. So I'm going to extend this out 1. So it's the 0.63. But then again, if you look at what the picture looks like, it curves up like this. So let's look back at it. Okay, so if you don't have a graphing calculator at home, remember what I said the first week. You can find free graphing calculator software on lots of different sites. My favorite one, the one I think that is most like the TI calculators, is Desmos. But you can find others. okay? But you should be able to come up with some graphing utility you can use at home, okay? So let's look at this graph now that we sketched it, okay? What do you notice about the vertical asymptotes? There are two, right? And every piece of the graph gets close to them without doing what? Touching or what? Crossing, okay? But the horizontal asymptote, do you notice that the middle kind of breaks the rules a little bit? Like the middle is not really getting close, right? It's actually kind of staying away. But what about the ends, the far left and the far right? Are they getting close to the horizontal asymptote without actually crossing it? Yes, okay? So my point is the middle piece is kind of a rule breaker, okay? Actually, the middle piece could have crossed through it. There are some graphs that cross through it, but it never will at the ends, in other words, the far left and the far right. So think about like vertical asymptotes are like severe rule followers, okay? Horizontal asymptotes are kind of like, okay? Only the far left and the far right have to follow the rules, okay? The middle piece kind of gets to do what they want. Okay, so let's look at maybe a word problem kind of application of these types of functions, these rational functions. All right, so let's say that there's a company making skateboards that has a fixed cost per day of $200. What does fixed cost mean? Stays the same no matter what. So if they make one skateboard or 1,000 skateboards, their fixed costs are steady at $200. And then let's say there's a total cost of $3,800 per day. When 20 boards are made. So I'm going to ask you to take this information and we're going to see if we can do a couple of things here. So the first thing I want you to do is write a linear total cost equation. So that's the first thing we're going to do, and then we're going to use that for some other parts of this problem. Okay, so if I'm asking you to write a linear cost equation, then we're going to call cost C of x. So instead of y equals, we're going to use function notation. C always represents cost. But we still want to make it look like y equals mx plus b. Okay, because that's our standard form. That is our slope-intercept form. Okay, so what's going to go here? The slope goes here, right? And what goes here? The y-intercept, right? Because mx plus b, that's what it means. Okay. But I say we already actually know one of them. Okay. So what do you think the 200 represents? So I'm going to go through and underline what we need to know. There are 200 per day. And then 3,800 per day when we make 20 boards. So those are kind of the significant pieces that we need to pull from that word problem. Okay. So let's start with the fixed cost, the $200 per day. So which of those letters would represent the thing that's getting added no matter what? B, right? So B is going to be 200. But I still need to find M. In other words, I need to know what the rate of change is per board. Okay? So maybe I can use some of the other information to figure that out. By the way, it's not 3,800 per board. Like, that doesn't make sense, right? It's 3,800 total for making how many boards? 20 boards, right? So let's think about that for a minute, okay? So if we kind of work it off to the side, we have $3,800 total cost. Okay, and of that, $200 is the fixed cost. So I'm going to subtract that, okay? And the $3,600 is actually what's left for the cost of 20 boards. So the reason I subtracted it is because the 200 is happening no matter what, right? It's not really part of the per board cost. Okay? So we have 3,600 left for the cost of 20 boards, and then if I want to know the per board cost, what could I do with 3,600? Yeah, so now I'm going to divide 3,600 divided by 20, okay? And that's going to be $180, and that's going to be my per board charge or cost. So in other words, what is this representing then? This is my slope, okay? So I've got B is 200. I know slope now is 180. Okay, so now I can come up with a cost equation, and then we'll stop and make sure we think it makes sense. So it looks like it's 180x plus 200. So what's one way you could check yourself to make sure that you think you came up with the right equation? Yeah, plug in 20, and what kind of total cost should you get if you did it right? You should get 3,800. Notice you would, right? You'd get 180 times 20, which would be the 3,600, and then plus 200 more would be 3,800. Okay? So just so we're clear, we're going to talk about this later on throughout the semester. This is what we call fixed cost. We already discussed that. But this is what we call variable cost. Variable, the word means that it changes. And the reason that's a variable cost is because if you make one board, it's 180 extra bucks. But if you make 100 boards, it's whatever 180 times 100 is, right? So like 18,000. Okay, so for part B, let's say that I wanted you to find an equation for the average total cost per board. So this is something that in Business Math 2 you're going to talk a little bit more about, but I think we can use logic and reasoning to actually figure out an equation for ourselves. Okay, so the first thing is when I want to talk about average cost, we don't want to use C of X because C already stands for just regular old cost. Okay, so average cost in economics and business math, we use C with a bar over it, and you literally say that is C bar of X. Okay, so this is going to be a formula, like I said, you use in the next class, but let's see if we can figure it out. Okay, so ignoring X's and all that good stuff, what would you need to know the average cost per board? You would need to know how much the costs were, right? And you would need to know what else? How many boards you made, right? That's what you would need to know. What would you do with those two things? You would take the average cost and you would do what? Divide by however many boards you have, right? So that means if we want C bar of X, we just need to take the cost equation, whatever it is. In this case, it's 180X plus 200. And then we just need to divide by however many items we have. Okay. So in other words, we are essentially doing just what we just said. We are taking total cost and we're dividing it by the number of boards. Okay, so here, what's our cost equation, or our average cost equation? So here we have C bar of X, and it's going to look like 180X plus 200 over X. But in another circumstance, if the cost equation was different, you would use that cost equation divided by X. Okay, so for this one, let's look at the graph, and we're going to find the horizontal asymptote. So I'm going to show what the calculator can kind of help us with, and then maybe what it can't help us with. Okay, so let's, you don't have to, Charge my batteries. You don't have to enter this in. You can just kind of look up here if you want. So notice I have something with more than one piece. So what do I need? Where do I need parentheses for sure here? You need it on the top. You don't have to have it on the bottom. So 180x plus 200 divided by x. I don't know why I couldn't find that button. So notice if you graph it, it is, by the way, this means it's working. I don't know if you can see the little thing that's circling around. It's kind of unable to show me all the graph. How come? Why do you think that is? The numbers are quite large, right? So you need to know how to kind of adjust your calculator. So I'm going to zoom out. In other words, I need to be going more than just from negative 10 to 10, which is all this graph shows right now. So I can kind of zoom out if I want. That may or may not be enough. Notice, not really quite enough yet, maybe, right? So I'm going to zoom out one more time. So notice you can kind of keep zooming, but your calculator struggles to show you details at this level, right? Like, I don't think that shows you a lot of detail, right? I don't think it's really all that helpful, okay? So if we want to look at the graph, we wouldn't necessarily really be able to do that here, right? It's not as helpful as we would like it to be, okay? But luckily for us, we have another way to find the horizontal asymptote, right? So let's take a look at our equation again. Okay, so that's not me, dogging on the calculators. They're great. They do a lot of things, but they can't always show you graphs that are really, really large, even when you zoom out. All right, so what do we notice? Even though the numbers are large, how do we find horizontal asymptote? We compare the powers where? Of the top and the bottom, right? So the powers of the numerator and the denominator are what? The same. So my question first is, do we have a horizontal asymptote? Yes. Okay, and what would it be? 180? So the horizontal asymptote is actually y equals 180 over 1, or just y equals 180. Okay. So essentially what that's telling us is our cost graph is going to get closer to 180 the more boards we make, right? And that actually should make sense to you, okay? So let's think about that like in logical terms, just because this is a business math class, okay? If you make one board, that one board has to shoulder the whole fixed cost, right? That one board has to pay for, the whole $200 fixed cost. So do you ever watch like Shark Tank or any of those shows, right? The prototypes of any item always cost the most. How come? Because it's the first one and it has all the fixed costs wrapped up in that one little item, whatever it is, okay? But the more you produce the items, the less that should matter because it's being spread apart over a whole bunch of things. In other words, if I made 100 boards, do you think you're going to care as much about that $200 fixed cost if I make 100 boards? No, in fact, each of the 100 boards would shoulder how much of that fixed cost if we made 100? Just $2, right? So the first one's super expensive, right? But if you keep making more and more, and then what if you make, say, 1,000,000 boards? Then the 200 is really insignificant, right? So in other words, it's going to get really awfully close to just the 180. The 200 is going to be insignificant the further you go out, okay? And frankly, that's why businesses like Walmart can sell you things cheaper than mom and pop businesses, right? They're selling millions, whereas mom and pop businesses might only be selling 100, okay? So it's just one of the facts of economics there. Okay, so we talked a lot about two distinct kind of graphs in this section. So just because we spent 2 days on it, I want to make sure and recap, okay? What were the two main types of functions? Today we really just talked about rational functions, but on Wednesday we talked about another kind. What was it? Do y'all remember? Polynomials, okay? So you need to make sure you know how to find the details and the information for both of them, okay? Okay, so at the end of class, I'm going to go ahead and stop the recording.